All right, so here we go. So 40 people. Yeah, it reminds me. All right, so here we go. So I don't know what I'm saying about that thing, but it matters who counts the votes, right? If the government has complete control anyway. All right, good thing they don't in America. So all right, so we take the old standard deviation and divide by the square root of n. Divide by the square root of n. So, in other words, let me give you a feel for that. It'll be super easy when we do a problem. You know, they'll tell us, well, you'll see the examples in just a minute. But let me give you a feel for that. Remember the 5 dice thing? If we roll 5 dice and we find the average, it's really likely to get an average that's somewhere around 3 or 4 when you roll 5 dice, right? You could get an average that's 5 or maybe 6, but that's really tough. You'd have to get all 6s to have the average be 6. That's super rare, right? What if it went up to 10 dice? What if I rolled 10 dice? Could you get an average of 6 now?
Yeah.
Would it be harder or easier than it was for 5 dice?
Harder.
Way harder, right? But if I rolled 10 dice, what would I have to do to get an average of 6? All 6s on 10 dice. Which is harder to do? Roll 5 dice and get all 6s, or roll 10 dice and get all 6s? 10 dice, right? So my point is, the bigger the n, the more it's hard to get the really high and the really low, the more that the thing spikes in the middle. The bigger the n. The average pushes it towards the middle. Do you feel that? If you had 5 dice, it would be a little more spread. But if you had 10 dice, it's going to be more spiked like that. It's going to push things to the middle. If you're rolling 10 dice, you're always going to get an average of 3 or 4 probably. Do you feel that? Is there a little bit of math feeling going on there?
Still a bell curve, though.
It's still a bell curve. It's going to central it more, though. Central limit theorem. The bigger the n, the more it centralizes things, right? The harder it is to get the extremes when you have a whole bunch. Does that make sense? So that's why the standard deviation drops for bigger n. Why am I saying drops? Well, you're dividing by it. What happens if I divide by a bigger number? If I take 100 and I divide by 2 as opposed to dividing by 10. If I divide by 2, I get 50. If I divide by 10, I get 10. Right? So the bigger number that you divide by makes the total smaller, doesn't it? If you divide by a bigger number, the total gets smaller. So you see, that's why n is on the bottom. The bigger n is, the less deviation there is. It shrinks it down, centralizes it. Do you feel that theorem? I want you to feel it. Do you feel the truth of that theorem? I want you to have math feelings. Do you feel that a little bit, right? Right? Well, why is there an n on the bottom? I don't mean the square root and all these, but just in general, it makes sense, doesn't it, that there would be an n on the bottom? Because the bigger the number of dice or the number of whatever, you're going to divide by a bigger number. When you divide by a bigger number, the total gets smaller. The standard deviation, the amount of deviation, gets less. It gets all centralized. Less deviation for a bigger number of dice or bigger number of whatever. All right. So hopefully you felt that a little bit. Let's move on. So the population has a mean of mu, is what they call it, and standard deviation is sigma. Blah, blah, blah. We know all that. Blah, blah, blah. Okay. Here's the requirements. We're all into this bell-shaped thing, right? We're all into this normal curve stuff. Well, what if a data set doesn't have a normal curve? What if data is not normally distributed? Can you still, everything we've done up to now, I don't know if you realize it, but pretty much everything we've done in the last 2 chapters is all dependent upon the fact that the data is a bell curve, is normally distributed. So what if it's not? What if it's not normally distributed? Well, if it's not normally distributed, like remember the dice, if you roll just one die, if you roll just one die, that comes out level, doesn't it? That's not normally distributed. That's not a bell. For one die, that's not a bell. But when I turn it into 5 dice, it becomes much more of a bell, doesn't it? So the answer is you just up the n. If some kind of a situation is coming out not a bell shape, then you just raise the n value. You just roll more dice. And the higher you go, the more it becomes a bell. As we saw in that little experiment we did, when we took the averages for 5 dice, it started to bell for us. So we just didn't do enough. So we didn't get a very pretty bell. But it started to go up in the middle and down on the sides, didn't it? So everybody catching that point? So here's the official statistics qualifier. If you do more than 30, now I didn't want to roll 30 dice, I was getting to be too much. But if you're, this is a rule of thumb. Generally, if you're doing more than 30, whatever, dice or, whatever you're looking at, we'll see the examples in a minute, that's going to make any data set become a bell, no matter what it was originally. You getting the idea there? So we're all about taking data sets that originally were not a bell, like individual dice to just level. And if you do enough of them, 30 or more than 30 actually, so 31 or more, it's going to become a bell. So now, if the original population is not normally distributed and n is less than or equal to 30, then it's not a normal distribution. Am I making any sense? Let me write it out real clear. So there's 3 cases. Case 1. If the original is a bell shape, meaning bell curve, then good. If the original is a bell, then it's a bell, we're done. If the original, case 2, if the original is not a bell, but we're using, I should say more than 30, then the average becomes bell-shaped. Case 3. The original is not a bell, and we're using less than or equal to 30. Small. They call that a small sample. If you're doing 30 or less, they call that a small sample, then it's just not a bell. You just cannot do that. You cannot assume normal distribution, bell shape. Normal distribution is the same as bell, right? Can't do that. So there's 3 cases. 2 of them allow you to use bell. If the original data itself is just straight out bell, then great. You don't even need to do anything about it. But if the original is not a bell and you use more than 30, you'll have a bell. If the original is not a bell, but you've got small sample, then you're out of luck. Is that making sense? We're all into making sure we're dealing with bell-shaped data. So how do we guarantee bell-shaped data? Either the original set was bell-shaped, or if it wasn't, we're using samples more than 30. Then that'll force it to be bell-shaped. What you want to watch out for is if the original shape was not bell, the original data was not bell, and you're using small samples, 30 or less, then you're just out of luck. It's not bell-shaped data. That's a little theory there on how statistics works. All the formulas been using. What is it? Cum, whatever it is, all those inverse norm and cum, norm, cum, what is it? Norm, CDF, he knows names better than me. Whatever they are, I'm thinking cumulative, whatever they are, none of those work. You can type the buttons, but they're all baloney unless you've got bell-shaped data. That's all based on bell-shaped data. All right. So practically, what do? When working with the mean from a sample, you got to verify that it's more than 30. And yeah, we don't need to worry about this stuff. We'll see in the examples. We don't need those formulas. We have the calculator. All right, here we go. We'll look at one example, then we'll dive into the homework. The elevator in the car rental building at San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds, 27 passengers. 4,000 pounds, 27 passengers. This converts to a mean is average, right? Passenger weight of 148 pounds. That's a little low when the elevator is full. We will assume a worst case scenario in which the elevator is filled with 27 adult males. Do you think if that elevator has 27 adult males, it's likely to be under the weight limit? No. The average weight's 148. Not likely, huh? Assume that the adult males have weights that a mean of 189. That's the average weight. Standard deviation 39 pounds. Find the probability that one adult male has a weight greater than 148. And then, part B, find the probability that 27 randomly selected adult males has a mean weight greater than 148. All right, 2 questions. Notice the difference. In case A, it's one person. Case B, it's 27 people. That's what today's about, is groups of people. What we did Monday was one person at a time, like part A. All right, let's do it. So part A, how will we do part A? Well, bless you. So, they're doing part B there. So, all right, so we can do part A. So, so let's use our calculator. So, I'm just going to do part A right here. So, part A, what is it? 148 pounds. So, probability, one person weight is greater than or equal to, what is it, 189 or 148? Greater than or equal to, 148. The mean weight for adult males, and they say it was 189? And the standard deviation, what did they say? 39, yeah, 39. Okay, we good there? You tracking with me? So this question you already know how to do, right? This would be what we did last time. They say, hey, we've got the average weight for adult males is 189, standard deviation 39, so much deviation. What's the chance if you grab one adult male at random that their weight's going to be 148 or more? Can we figure that out? So I'm going to do one of those two things we learned last time. How do you know which one? Do I want to know the percentage up here or the number on the bottom? Probability. What's probability? That I should have written that word all the way out. The probability. What's probability always? Is it a percentage? Yes. Absolutely. Yeah. So I want to know the percentage. So does that mean I want the stuff in the top of the curve or the bottom? The top is always percentage, huh? Top's always percentage. The bottom is not percentage, right? So I want to do the normal CDF, right? Because the bottom is the inverse, right? Normal CDF. And what do? We do left, comma, right. So what's the left edge? Here's 148, notice. And then what's the right, of the shading, see the shading here? 148's the left edge, what's the right edge? 999, right? So 148 is the left edge, 999 is right, that's left, right, mean, 189, standard deviation, 39. Hit the buttons on the, we're going to get 8531?
Yep.
Nope. Yep, nope. Nope. Well, that's funny. It came out a little different, huh? We got 8534.
Yeah.
Interesting. We'll just call it close enough. All right. So basically 85%. So that means there's an 85% chance that you grab an adult male at random, he's going to have weight 148 or more. Makes sense, right? If the average man's almost 190, then there's a good chance if you grab somebody, they're going to be 148 or more, adult male, right? So 85% chance, basically. We good there? So that's nothing new at all. That's exactly what we did Monday. Now, question B is going to say, same question, but we're not just wanting to grab one adult male. We want to grab, was it 27?
Yes.
27 guys and average their weight, like averaging the dice, average the weight of 27 guys. What's the chance that the average of their weight? Now, do you have a feel before we go? I want to do all I can to build in math feelings. So that'll help you, because we all hit wrong buttons on our calculator. But if you have feelings, then you'll know when you've hit a crazy button. You'll just like, there's no way that's the answer. And then you'll be able to go back and go, I must hit the wrong button. So tell me, just going in, let's start to develop those feelings for a minute. If I said, how about this? Bit of a feel. Let's actually do it. So what are we going to do? We're going to do exactly the same thing. The only difference is the standard deviation will change. It's super simple mechanically. It's what was the other standard deviation? 39?
Yes.
You just take the other standard deviation and you divide by the square root of 27. I would literally just put it in just like that. Everything else is the same. So I'm going to go normal. It's the only difference. That's the only difference in this whole section. So normal CDF, is that what it was? Yeah, normal cumulative distribution function. What was the left edge? 148, 999, that's all the same. 148, 999, what was the mean? 189. And then when you come to standard deviation, just go 39 divided by square root of 27. Hit the button. You should get something really high. It's probably like 100% or something. I don't know. Is that coming out? What'd they say? Yeah, they got 0.999999998. So, yeah, divided by, everybody see this divide here?
Oh, yeah, that's 99%.
Yeah, so that's 30, it would help if I wrote it this way. 39 divided by the square root of 27 in that last slot. So that's the only difference today. If you have a group that's bigger than 1, you divide the standard deviation by the square root of the group number, the group size. On that. Nurdine.
Do we do the same thing when we got to the inverse now?
Yeah, it'd be the same thing. Yeah. Is that coming out? You guys getting like 0.99999?
Yeah.
Bunch of nines like that. Is that coming out okay? You able to get that in the TI? So there's hardly any difference. You just divide by the square root of the group size. Because there's less standard deviation. Things tend to the center. Central limit theorem. We good? Questions? All right. I'm going to move on. Let's get to the homework, huh? I don't want to do the safe loading one. Oh, we did it. All right. On to number 1.
So you're punching in the square root of, like, how would you punch?
Let's try number 1. Here we go. A researcher collects a simple random sample of grade point averages of stat students, and she calculates the mean of this sample. Under what conditions can that sample mean be treated as a value from a population having a normal distribution? In other words, blah, 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 is this a normal distribution? Is it a bell? That's what they're asking. Remember that talk I did about, I gave you the 3 conditions? That's what they're asking us about. They're saying, when can data be bell-shaped? Select all that apply. It's going to be more than one answer here. Let's go through it. What does it take to make sure you're dealing with bell-shaped normal data? Let's say, if the population has a normal distribution, if the original population, for sure. Yeah, if the original population is normally distributed, great, we're good. We don't need anything else. Next, there's more than one answer here. The sample has more than 30. Yeah. If the sample has more than 30, it doesn't matter what the original was, that'll make it bell-shaped. C, the researcher collects more than 30 samples. Oh, I'm getting confused.
I think the top one was for like a certain number.
The sample has more than 30 grade point averages. The researcher collects more than 30 samples. No, it's B and not C. Yeah, you understand the difference. So there's a whole bunch of statistics students out there, and the researcher grabs a number, right? A sample, the sample, one sample that is a sample that is 30 grade point averages. Averages them all together, right? The sample comes from 30 grade point averages. That'd be like me saying, I rolled 30 dice and got the number. You got the average of 30 dice. That'll make it bell-shaped, right? Whereas C is saying something different. They're being subtle here. The researcher collects more than 30 samples. That'd be like me rolling the single die 30 times. And not averaging. That's not going to do it. See the difference? It's not 30 rolls. It's an average from 30 dice. That's the key difference there. It's one sample of 30 grade point averages, not 30 different samples. And so D, the population is of grade point averages has, wait, I thought that's what we already said. If the population of grade point averages has a normal distribution. What did A say? If the population, of statistics students. No, sorry, I didn't read it carefully. It's not A. It's B and D. They're being very subtle on this one. It's the grade point averages that have to be normal. Not the statistics students. I don't know what it even means for a student to be normally. What, their heights? Their ages? What does that even mean? Are the students normal? What about them? Their height, weight, hair length? What? See, that they fooled me. It's not A. Does everybody see what we're talking about? You can't just say the students. You got to say something about them, like their GPA or their whatever, their age, their whatever. So it's B and D. All right, that was a tricky one. All right, let's go on to number 2. Having thoroughly confused you, right on to number 2.
It's official.
All right. Weights of golden retriever dogs are normally distributed. Samples of weights of golden retriever dogs, each of size 15. 15. They're taking sample size 15, are randomly collected, and the sample means are found. Is it correct to conclude that sample means cannot be treated as being from a normal distribution because the sample size is too small? Is that true? So what's the deal, Eddie? Why not, Nurdine?
It says no, the original population is normally distributed, so the sample means will be normally distributed.
So what does that mean?
Shit.
Do we know what that means?
Well, it's a normal distribution, is the number's gonna be counted, isn't it?
So remember, why are we trying to take bigger numbers? Let's go back to the whole reason we're even doing this. Why did I want to do 5 dice or 10 dice instead of just 1 die?
Bigger numbers, more simple.
Bigger numbers, it'll make it a bell even if it wasn't originally. Remember?
Right, yeah.
So if it's not a bell originally, like 1 die at a time is certainly not a bell originally. If you take groups, averages of groups, then it becomes a bell. So the whole reason we're taking averages of groups is we want to take something that wasn't a bell and make it a bell. We got to have a bell for all of our formulas we use. So if the original, the weights of the dogs are normally distributed, if the original already is a bell, then who cares what size you take? We already got a bell. You get it? And it centralizes it more. But it makes it a bell and centralizes it more. Does that make sense? Yeah. So in this case, so that's what you got to watch for. That's what they're going to play with you back and forth. They're going to say, are you getting it? If the original data is already a bell, already normally distributed, then we don't need to take any certain size. We're already a bell. The only time you really need that is if the original population was not bell curved. Then you need to take more than 30 and it'll make it bell shaped, central it, right? All right, so this would be, so what's their question then? Is it correct to conclude that we cannot treat this as normal? No. We can treat this as normal. No. The samples are collected so that random. So what? I'm so confused. Oh, that's not the right one, is it? There it is. They're really tricky on these things. The original population is normally distributed, so it's all good, right? We don't care about the fact that they only had 15. That's what they're trying to trick us on. They're giving us less than 30, saying, is that a problem? And we're saying it's not a problem because the original already was a bell. We didn't need 30, more than 30 to bell it. It already was a bell, right? All right. Number 3, the overhead reach distance of adult females are normally distributed with a mean of 205.5 and a standard deviation of 8.9. Find the probability that an individual distance is greater than 218.00. An individual distance. So they're first asking me about an individual distance, notice. Then they're going to ask me about an average, a mean for 25 people. Right? So it's just like the question we did in the lecture example. So can we do the individual first? You guys have your calculators? Yeah. So crank out the individual one first off. We got a mean. We got a standard deviation. Greater than 218. If you want to draw a bell curve, that might help you. All right, so greater than 218. So if you don't have to draw a bell curve, but it might help. What's the middle?
205.
So the 205.5. That's the middle. So then 218, is that to the right or the left?
Right.
218 is a little bit to the right, huh? Like over here. And they're asking greater than 218. So do I shade to the right of it or the left of it? Right. To the right. So they want to know this part to the right of 218, huh? So what's the left edge of my chunk of shading?
218.
Yeah, the left edge is 218. The right edge? The 999, huh? We good? So it's normal CDF. Well, I'll put right here. Normal CDF. Left edge 218, right edge, 999. Middle, mean, 205.5. Standard deviation, just the 8.9. We don't put anything else in right now because we're only doing one person. Hit the buttons. What'd you guys get?
8%.
What'd it come out?
8%.
8%, 0.08. Rounded. Oh, it says 4 places. What did it?
80800.
0.0800? 0800 is around to 1. 0801. We good? Good now? 0801, okay. And now part B, same exact question. It's just now for the average of 25 people instead of just one person. So what are you going to do differently on part B? Hardly anything, right? It's normal, CDF. All the numbers are the same except what?
Do they got that lower and upper?
Lower and upper are the same. What's the only thing that's different?
The upper is 204.5, isn't it?
Yeah, the lower.
Greater than
Yeah, so the
204.5.
lower is gonna be 204.2.
Oh, I didn't notice they changed the question. Oh, my mistake. Yeah, I thought they gave the same question. Yeah, you're right. They 204.20. Yeah, they went right here, huh?
That's the lower, right?
I didn't notice they were changing. Yeah, that's the lower for sure. Yeah.
And 999 for the upper.
Right. Yep. You're right.
So standard deviation is still 8.9?
No.
Standard deviation is,
So what do we do for the standard deviation? We take the old one, 8.9, divided by the square root of 25.
117.
0.5117?
I got a question. How would we do it on this calculator? Because you gotta like. Yeah.
Okay, so I'm getting 0.7674, yeah.
So what numbers you punch in?
All right, so we got the 7674. What about question C? It says, why can normal distribution be used even though we only have a sample of 25?
Normally distributed.
Remember? Because you remember the rule? It said take more than 30 and it makes it Bell. We're not taking more than 30. We're only taking 25.
There's already a bell to start with?
It was already Bell. Did they say that?
Normally distributed.
Normally distributed.
Normally, right? Overhead reach distances of females are normally distributed. It was already, same thing, right? It was already normally distributed. There it is, D, at least on mine it's D. The original population has a normal distribution. It's already Bell. We don't need more than 30. All right. On we go. So that's the same thing. How about I move on? 5. I'm going to go to the more interesting ones now. All right, so 5 will be a little more interesting. Elevator has a placard. So here we have an elevator one again. In fact, why don't we just, how are we doing on time? I want to make sure I cover that last section. We're okay, all right. Elevator has a placard, maximum capacity, 1,204 pounds, 8 passengers, 8 adult male, blah, 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 163. Probably the elevator is overloaded. Probably the elevator is overloaded. Like Mai says, there's a lot of means in there. That is the battle to straighten all those out. So let me help. So one thing you could look for is their question. They're going to say, find the probability that it's greater or less than a certain thing. Where do they actually say that?
It's,
Where do you see the word greater or less?
greater than 163.
Greater.
Yeah. So that means on the curve, it's going to be 163 or greater. So that's the left edge, right edge is 999. Good how you can nail that down real quick. Just look for that phrase, greater or less. So when you find that, Leonardo. Yeah, my test on the test, they're always just like homework. All right, so 163 to 999. Is that good how we found that? And then what's the overall mean for the data set? What's the middle? Does it say that anywhere, mean?
173.
173. Right, good? So now we're going to do
But how
normal CDF.
could the 163 be in front of the?
Oh yeah, I just did it badly. It's actually, you're right. It's actually in this. I didn't know, I was just guessing in the beginning. I probably should have started with the normal.
Right.
But yeah, it's going to be on the other side. What is it, 163? Yeah. 163. It's still true though. It's still going 163 is the left edge. 999 is the right edge. The mean 173. And what do we do for the standard deviation?
30.
What they say it is? Oh yeah, standard deviation, there it is. 34, yeah, 34, but you got to divide by the square root of how many people? 8 people, yeah.
Yes,
Is that making sense there?
and then 9999 would be your reference.
And let's see what we get. I'm getting 0.7973.
Yeah.
Coming out. How are we doing? So do you see how to identify the different things? So there's the overall mean, 173, that's the middle. And then there's the greater than, less than, question greater than 163. So left edge, right edge, mean, standard deviation, divide by the square root of how many people?
Oh, man, I forgot to go.
Is that good? Questions I can answer? All right, let's try another one. Ski gondola. Carry skiers to the top of the mountain. So the weights, normal distributed, mean, standard, gondola, 25 passengers, load limit 3750. Given that the gondola is rated for a load limit of 3750, what is the maximum mean weight of the passengers if the gondola is filled to the stated capacity of 25 passengers? So let me let you think on that. What are they asking us? What do we do in part A? Anybody have an idea on A?
So you do the normal CDF.
Yeah, good. Yeah, I think we're overthinking it. You see what it is?
You just divide 3,750 by 25.
Exactly. They're just saying you've got 3,750 pounds load limit, 25 people. What's their average weight have to be? Right? If the total weight on the gondola is 3,750 pounds for safety, and you got 25 people, what does each of their weights have to be? What's their average weight? Just divide. 3,750 divided by 25. I'm getting 150?
That's your mean.
That's the average weight per person. If you have 25 people, if they weigh 150 on average each, then you'll meet your load limit capacity.
150.
That doesn't seem very safe. At least if they're all men. Does that make sense there? Question B. If the gondola is filled with 25 random skiers, what's the probability that their mean weight exceeds? So what if they have this gondola that has, this 3,750 pound limit weight, 25 passengers? What if 25 people pile onto this thing?
There's no. Oh well, the
What's the chance that their mean weight exceeds the value we just got from part A. So let's draw a normal curve. What's the middle of the curve?
Mean or 193?
193, right? The mean is 193.
So it'd be
Means 193. So now, that's the mean of the whole thing. And they're asking me, what's the chance that it exceeds what we got in part A, exceeds the 150? What's the chance it exceeds 150? So where do I do? How do I put the one? Where does the 150 go?
150 is your left,
Over here?
9999 is your right.
Yeah, exceeds means to the right, huh? Exceeds means greater than?
193 is your mean,
Yeah.
and then
So rest good? Can I just go dot, dot, dot on that?
38 divided by square root of 25.
Right. You want me to write it out?
Yes, please.
Normal CDF. Normal CDF.
150.
Right? So you always go left edge, right edge, mean, standard deviation. So left edge, 150. Right edge,
999.
mean, 193. And standard deviation, did they say?
193.
No.
38, right?
38, so
That's
38
standard deviation. Oh, yeah.
standard deviation is
Divided by
square root of 25.
square root of 25. Because there's 25 people, huh? Does that make sense?
99999.
Is that what it is? Not 100%. In other words, for sure, you're going to overweight that gondola. That's not a good plan that they have, right? They didn't think about their statistics ahead of time. All right, if the weight, so they're just going to change it to another question. I'm going to move on. I want to get to the next section, make sure I do a good job. So on that, how far do we go here? 7, 8. Okay, good. Just 7 and 8. Okay, 7. Yeah, 7 will be a little different. Let's do 7. And engineer is going to redesign an ejection seat for an airplane. The seat was designed for pilots weighing between 130 pounds and 191 pounds. The new population of pilots has normal distributed weights with mean 137 and a standard deviation of 28.4. That's a light average weight. If a pilot is randomly selected, find the probability that his weight is between 130 and 191. Question B, if 33 pilots, find the chance that they're average. And then part C, blah, blah, blah. All right, let's do part A. Part A. So I'd encourage you, so part A, draw the bell. Fine, and what's the middle of the bell? Does it say mean somewhere?
Yeah, 137.
37.
Oh yeah, there it is, 137. I can see better on that screen than I can on my iPad. 137, yeah. Okay, and now, what chunk do they want me to find? Where do they say greater or less or?
Between.
Yeah, they say between, don't they? Between 130 and 191. Where's 130? A little bit left. And then 191 is way over here. So they want all that, don't they? So that's the left and right edges of my shading chunk, huh? So then we just dive into the normal. CDF. Left edge, right edge, mean, standard deviation. It's getting easy? Getting me like same every time almost? Slight variations. Left edge. 130. Right edge.
191.
191. Mean
137.
and standard deviation.
28.
Yeah, did they give me that? Where is that? Oh yeah, here it is, huh? Yeah, 28.4. Now, do I divide?
No.
I'm doing part A. Part A is
One.
a pilot. Yeah, only one person, huh? So we just have it like that. Somebody got that number?
It's 0.5687.
0.5687? You sure it's not bigger? That could be, I guess. Oh, yeah, no, that's right. Yeah, that looks good. Okay, and now on part B, the only thing they're, well, I think, yeah, same 130 to 191. The only thing they're changing is now it's 33 pilots, and we want the mean weight, the average of 33.
So you square root, of the
Yeah, you just divide by the square root.
28.4 divided by square root of 33.
Yep, everything else is the same. Normal CDF, 130, 191, the mean is 137, and then 28.4 divided by the square root of 33. And so we'll get what will we get? Remember, it tends to move things towards the center, doesn't it? So if it's moved towards the center, it's more likely to be there. It's going to be really high probability.
92.
Po-
9215.
0.9215?
9416.
Oh, round to 6? Okay. So it's much more likely that the average of 33 pilots is in that zone because it centralizes things when you take a big group average. So when redesigning the ejection, here's a real life question. I mean, they're trying to make sure we're dialed in with reality. When redesigning the ejection seat, which probability is more relevant? Which of those answers, the answer to A or B, is more relevant? This is where you want to step back and make sure you're getting the big picture. Like, why would they even do this? Why would they even care? Why in the real... So make sure... What are they doing here again? They're designing an ejection seat. They made it to work for people whose weights are between 130 and 191. So you got to be in that zone. You got to be pretty light for it to work. And they're saying in Part A that 56.87% of pilots have a weight in that zone. In Part B, 92% of pilots, well, if you take 33 pilots, the average weight, there's a 92% chance it's in that zone. So which percentage would matter? If you were the design team, which percentage would you care about? And why?
The 56%.
Why is that?
Because it's about like half per pilot. So like that's like there's a probability like most people won't meet the requirement.
I think you guys are thinking too mathematically. Actually, let me give you a hint. It has nothing to do with those numbers. It has nothing in the world to do with these two numbers. Nothing at all. It's just real life. Just think real life. You guys are too mathematical. Just think real life. Just think real life. What an average is. So let's see. I'm hoping they say that. After saying all that, I hope they say that. I didn't look in advance. So it should be Part A. Why is the answer Part A? Again, having nothing to do with that number, just because that number is about an individual. A single pilot sits in the seat, not a group of 33. We don't care what the average for 33 is. We care that the individual in the seat is in that zone, right? That's what we care about. So let's see. The answer should be Part B because seat performance for a sample, no, not a sample, because seat performance for a single pilot is all that matters.
But it's Part A, right?
Oh, is that? Oh, yeah, I did Part B. Yes, after saying all that, it's Part A. You're right. Which one is? They always fool me on these things, don't they? Is it this right here, I think? Yeah. Try one more time. Single pilot, Part A. Good, that's what I wanted. Make sense? It's easy to get lost in the numbers. All right. All right. We are ready to wrap this section up here. Boat. That's probably the same. It is. All right. I'm going to move on.